Assalamu alaikum. Hope you are doing fine. We have learned about electric dipole and its properties in the previous video. In this video, we will learn what happens when an electric dipole is placed in a uniform electric field. We know an electric field in which electric field lines are parallel to each other is referred as uniform electric field. I consider this one as a uniform electric field. In this, I place a dipole. We know an electric dipole is made of two equal and opposite charges separated by a small distance. The distance usually between two opposite charges is taken as 2a. Here, I take the midpoint of this electric dipole as O. This point where the negative charge is placed is named as A, and this point is named as B. Here, negative charge is represented by letter minus Q and the positive charge is represented by letter plus Q. The distance between O and B is taken as A. Similarly, the distance between O and A is again taken as small a. So the total distance between A and B is 2a. Now, we know if we have two charges, suppose a positive charge and a negative charge, then the electric field lines start from positive charge and intersect a negative charge. This we have learned long ago. This is the direction of a electric field line, and these electric field lines constitute an electric field. Similarly, here we have electric field, and the direction of this electric field is represented by this arrow mark. This indicates that the electric field lines have started from this point and ends here. That means here we have a positive charge and at this end we have negative charge. If it is so, due to the negative charge, this positive charge of electric dipole is getting attracted. It experiences an attractive force. So, the force experienced by this positive charge of electric dipole is directed in this way. Okay, and the force experienced by negative charge will be acting in this direction towards the positive charge, which has produced this uniform electric field. Anyhow, what will be the expression of these two forces? Let's find out that. We have learned this long ago in this chapter. We know electric field is nothing but force per unit charge. From this, if we cross multiply, we get this Q E vector. This is the expression for electric force. Now this is the force. This is the force experienced by these two charges in two different directions. Here, the force experienced by positive charge is plus QE vector, and force experienced by negative charge is minus a q e vector. Okay, and one more thing you need to know. Here we have electric dipole, so definitely there will be electric dipole moment represented by letter p vector. P vector. Okay. This electric dipole moment always act from negative towards a positive charge. I repeat, electric dipole moment acts from or points from negative towards a positive charge. From negative to positive, it points. This is known to us. So this is the direction of electric dipole moment, represented by letter P vector. Clear? Okay. So from this diagram, it is quite clear that there are two forces acting on this electric dipole. One towards the right side, another towards the left side. So these two forces usually referred as couple. Remember this, two forces acting in two different directions is referred as couple. Okay, so a couple of forces acting on this electric dipole. Because of this, what happened? This force is trying to move this electric dipole towards the right side, and this force is trying to move this electric dipole towards the left side. So as a result, they cannot move this electric dipole along the line, along the length, in simple words, because both of them have the same magnitude. Instead, what happened here? Because of these two forces, the electric dipole starts rotating in a clockwise direction. This is the clockwise direction. Correct? And the measure of rotation of any object is referred as torque. I repeat, the measure of rotation of any object is referred as torque. And for the motion, what is required? Force. Here we have these two forces which rotates this electric dipole. Clear? Now, my aim is to get the expression for torque experienced by this electric dipole placed in a uniform electric field. We represent torque by letter tau. How do we read this? It is read as tau. Tau. Tau represents the torque. It is a vector quantity. It's a vector quantity. Now, look carefully how I am going to get the expression for torque. Torque is usually obtained by multiplying the perpendicular distance between the forces and the magnitude of any one of the force constituting couple. Okay, here we have two forces. We take the magnitude of any of these two forces and multiply that with the perpendicular distance. So how to get the perpendicular distance? Look at here. If you look at these two forces, both are acting in the same line. This is a line. It is acting in this line and this is acting in the same line, but in opposite direction. Okay. Now if I drop a line perpendicular to this, then that line will provide us perpendicular distance between two forces. Let me do that. See, This is a line. This line is perpendicular to this force as well to this. Clear? Now, the length of this line is actually provides as the perpendicular distance between these two forces. Now, how to get that? It's too simple. Now, here, see, this electric dipole is inclined at some angle. I denote that angle by letter theta. Theta is the angle between the electric field and the electric dipole. Okay, if it is theta, then this will also be the same. This one is also theta. This angle will be theta. Now, if you look at this diagram carefully, it appears to be a right angled triangle. Okay, so to get this, and then this point as C. Name this one as C. Here A, B, C. Then we have a right angled triangle A, B, C. Okay, that I take this right angle triangle. This A, this B, and this point is C. This is the opposite side. Now, the side of right angle triangle present opposite to the angle is called as opposite side. This hypotenuse, and this one is the adjacent side. Okay. For this, what I do, I find a sin theta. What is sin theta? Is opposite side by opposite side divided by hypotenuse. What is the opposite side? Is not known to us. Actually, I am doing this to get the value of opposite side. So I keep this as such. Hypotenuse is hypotenuse. Its value is known to us, and it is nothing but 2a. What is this? 2a. And I mentioned here it's 2a. So from this, opposite side is equal to 2a sin theta. Clear? 2a sin theta. I box this. I'm going to do this one here. So this perpendicular distance between these two forces is nothing but 2a sin theta. Clear? Change the color. As I told you earlier, torque is the product of perpendicular distance and the magnitude of any one of the force. So, magnitude of any one of the forces multiplied with the perpendicular distance. Perpendicular distance. This is a symbol for perpendicular. Perpendicular distance. Perpendicular distance. Okay. So magnitude of any one of the force, we have two forces. Torque is represented by letter tau. Symbol is tau. Magnitude, we take modulus Q E. Vector is multiplied with the perpendicular distance. That's 2a sin theta. So this can be written as QE to A sin theta is tau. Fine. This I represent here. Now I rearrange it. This equation I write it as 2QA E sin theta. Right? Then this can be written. See, we know A vector cross B vector is nothing but A dot B sin theta. By keeping that in mind, here what I do, I write it this way. This I do the reverse thing. Now here, this one is taken as A, this one is taken as B sin theta. Then, one more thing is known to us. We know 2QA is nothing but P. What P? P is a electric dipole moment. So in the place of this, I write P. PE sin theta is nothing but tau. Yeah. Now, for this expression, I am going to apply this rule. So what I get this. AB sin theta is written as A vector cross B vector. This is the way. P sin theta is written as P vector cross E vector. Now tau is a vector quantity that I mentioned here. This is here as well. So this provides us the expression for torque experienced by an electric dipole placed in uniform electric field. Now if you look at this expression, I box this. From this one, it is clear that if the angle, suppose if theta is 0 degree, what does it mean? When I take a theta is equal to 0, that means this electric dipole is kept parallel to electric field. This is what it means. In such case, theta value is 0 degree and sin of theta is taken as sin of 0 degree, and that's nothing but 0. And in such case, if you substitute this one here, what will happen? Tau will become PE multiplied with 0, and the torque becomes 0 in such case. When the electric dipole is placed parallel to electric field, the torque experience is 0. You remember this. And the second thing, when it will be maximum, the torque experienced by electric dipole will be maximum when the angle between electric dipole and the electric field is 90 degree. It is at 90 degree. It's 90 degree. Sin of theta is equal to sin of 90 degree, which is equal to 1. So in such case, in the place of sin theta, we substitute this. Tau vector is equal to PE into 1. That means, when happened is PE. Clear? So, when the electric dipole is kept perpendicular, the tau value is maximum, and it will be 0 when it is kept parallel to electric field. You remember this. Okay, now I will tell you what happens when the electric dipole placed in non-uniform electric field. When it is placed in uniform electric field, it experiences a torque. Okay. Now dipole, electric dipole, in non-uniform electric field. You see what happened in such case. Now I draw a non-uniform electric field. Now, an electric field in which the electric field lines are not parallel is referred as non-uniform electric field. It is known to us. Now, this is a non-uniform electric field, and as I take a positive charge here, negative charge. So, this constitutes an electric dipole. This will put to O. This I take as A. This is as B. Here is a plus Q charge. This is a minus Q charge. So here in such a case, what happens? The direction of electric field is keep changing from point to point. No? Here the direction changes and also the magnitude of the electric field changes in a non-uniform electric field. It is known to us. So in this case, what happened? The force experienced by this charge will be acting in some direction, and the force experienced by this one is acting in some other direction. So definitely it experiences a torque. Along with torque, it also experiences a force, a net force. Remember this. So when we place the electric dipole in a non-uniform electric field, it experiences a torque. Apart from torque, it also experiences a net force. Okay. So here, instead of writing it as plus QE, I write it as plus QE1 vector. Here I write it as minus QE2 vector. Why E1, E2? The reason is the magnitude of electric field varies here from point to point because it is a non-uniform electric field. I hope I have understood. In a uniform electric field, an electric dipole experiences only torque, whereas in non-uniform electric field, an electric dipole experiences both a torque as well as net force. I hope the video is useful. If you have any kind of doubt related to the topic, kindly put your questions in the comment section. Thanks for watching.